adaptive mesh refinement for DG.
Exactly right. Providing this laptop is willing to cooperate. Yeah, okay. There it is. There it goes. All right. Thanks for the introduction, and thanks to the organizers for having me here and allowing me to talk to you about our adaptive mesh refinement algorithm, which we are trying to implement into our NUMA code. Our NUMA code basically, well, one of its options is the discontinuous Galerkin method, and we do it on quadrilateral grids. And I will discuss the approach we took for AMR, namely the non-conforming approach, in some more detail today, and show you some results. Now the motivation for that. On the left you see the rising thermal bubble problem, which you have seen today in Andreas' talk. And the right panel is the fully refined simulation. The left panel is where our AMR kicked in, and our goal was to bring down the number of elements so that we can pay a little price, or no price if possible, in accuracy, but still resolve this feature well, or any feature we would probably like. The ultimate goal, or the next step, would be to tackle slightly difficult problems, namely a hurricane simulation, something like that, where we feel that this adaptive approach could really work nicely. Probably this should work too. Yeah. Oh. There you go. So now, a couple of words about the approach we took. As Andreas explained nicely earlier today, in DG, most of the work we do within the elements, and the only thing that sort of glues the elements together are the fluxes. Now, constructing the AMR algorithm for DG, we need to consider, well, we need to make one very important decision. Either we'll try to keep our mesh, our elements conforming. That means each edge is shared only by two elements, and therefore the flux computation doesn't change. We can reuse our solver exactly the same way as we do with our regular grids, and then put the burden of AMR on the AMR algorithm, and then we can have like a separate algorithm for that. Or we can allow, or we can implement the non-conforming flux handling within our solver, and then keep our strategies for AMR super simple, so we are not worried about them too much. Well, since in our group we feel strongly about our solvers, we decided to go the second way and try to make our solvers handle the situation where we've got more than two elements per edge. And that's one of the main points of this talk. Now, we also adapted a forest of oak tree approach, which we heard about today as well. So just to maybe a quick recap, we start with a level 0 mesh, with a basic coarse mesh, example of which you can see here. In this case, it consists of 4 elements, and we can represent it as a tree. Well, each of those elements will be a root of a tree, which will develop within those elements. So if we decide to refine those 2 large elements into 4 small ones, our tree would look like this, and we can go further and further and further, and we can use this tree structure to efficiently implement this algorithm into the code. Now, of course, our level 0 mesh doesn't have to be a square or a rectangle or anything which is nice and easy. It can be something like this. You've got the Indian Ocean here. However, we want for now at least, we want our level 0 mesh to represent the geometry of our domain. So we need to, at the level 0 mesh, we need to have all the information about the domain we need throughout the entire simulation. And yes, well, this condensation of elements doesn't look that well, but we didn't try to run that yet. and we probably won't go as fine with level 0 mesh, obviously. And this, what I just said also applies to, for now at least, to bathymetry or orography. We do not have the capability to refine this feature yet, but it will probably come in the future. Also, a nice feature about living in a high-order world is that our elements don't have to be squares or rectangles. They can have curvilinear edges, and we can super easily divide them into 4 small elements. Just by we need to project all our elements into the computational domain anyways, and splitting a square into 4 small squares is a no-brainer. And then we have got the projection back by default, so that's not the problem. As I said, well, we divide each of our parent elements into 4 smaller elements all the time, and we also want to keep the 2-to-1 size ratio, meaning that each edge can be shared by at most 3 elements. So let's imagine that this red blob here is a feature around which we want to refine. And you can see this mesh here is nicely balanced. We say it sort of follows this 2-to-1 size ratio rule. So no edge is shared by more than 3 elements. But say if we want to move, if our feature moves somewhere else, we obviously would like to refine here. But then we run into trouble because those elements we don't want refinement over there, obviously, because our feature is not there yet. But because we want to keep the 2-to-1 size ratio, we still need to refine over there. So that's one of the downsides maybe of this approach, because we really want to keep this 2-to-1 size ratio for the reasons I'm going to discuss in a second. Right. So let's imagine we do have what we want, namely the 2-to-1 ratio phase. And now the question is, how do we compute the flux for DG? So let's start with a variable, whatever variable we like, QL, on the left. We've got variables, the same quantity QR1 and QR2 on the right, on the children elements. What we want to do is to project this QL into those elements here, so to have a representation of QL on both children elements or children edges. For that, we need to design some sort of projection matrices, which I will get to in a second. But let's assume for now that we've got them, so we can project that easily. Then we've got the conforming situation here, so we can easily, exactly the same way as we do in our conforming code, we can compute our flux. We've got F1 star and F2 star over there, and then again we assume that we have to construct some backward projection operation to project this flux back to our long edge, and finally apply the flux to appropriate element. Now there is a caveat here, because by default, in DG sense, flux here can be discontinuous at that point. However, we need to represent that on this edge as a continuous function somehow. And still this has to conserve mass, or basically anything, and to yield us a stable algorithm then. So how do we do that? Well, we use the idea of Kopriva 1986 of the L2 projection. So let's first focus on the scatter operation. So going from the parent edge to children edges. First of all, we define the coordinates xi, z1, and z2. Xi lives on the parent edge, z1 and z2 live on the children edges. Then we define mappings from xi to z and z to xi, and where s is the scale. In our case, it's always 1/2. And offset parameter is plus minus 1/2, depending on which child we're talking about. So, and now we play our usual game, namely we expand QL and in the in psi, in the parent basis, but we plug in our mapping so that we can represent QL in terms of those z coordinates. And we expand our unknown QL k in terms of z as well. And what we do, we require that for each children phase, so for each k here, 1 or 2, this integral is equal to 0. Namely, we take a difference of unknown variable QL k minus known QL, and we treat it with some test functions. And in this case, we choose our test function to be exactly the same as our basis function. And after substitution of the expansions, reorganizing, we get to the point where we can spot a couple of matrices popping out. And this one looks a lot like a mass matrix. However, it is not the 2D elemental mass matrix. That mass matrix is defined, is a 1D mass matrix defined on the edge only. And this integral is also along the edge, of course. And then this S matrix looks a lot like the mass matrix, but we've got this expansion plugged in over there. And this M never gets too big because our polynomial order can be 4, 6, 8, 10. Where's staging? 17, 16? Over there. So even if we want to invert 16 by 16 matrix, it's doable. And then because we keep this 2-to-1 ratio, we do it only once. So we design this projection matrix here only once before our simulation, and it doesn't and after that we just need to apply it, because at all scales the ratio of sizes is 2-to-1. In a similar way, we design the backward operation, so the gather operation. This time we design this QR tilde, which represents QR1 and QR2, but in this psi coordinate. And we again require that our integral now is equal to 0. After some calculus, we again get to a point where we've got now our gather matrix to be the scale times inverse of M times the transpose of our original S matrix. And again, we do it just once at the beginning, and then just apply this projection matrix all over again for any non-conforming phase. Now, for the result. So what you see here is the density current simulation, the regular Straka case. On the top, there is a fully refined case, and here you've got 3 different AMR simulations using different parameters for the refinement criteria. Now, what is the refinement criterion? Do not stone me, please, here, and throw any eggs. It's super simple. I just take the variation of theta, and whenever the theta variation is greater than a threshold, I refine. If it's less than that, I de-refine if I can, down to the coarses level. Keeping in mind, of course, this 2-to-1 balance. That's kind of important. So I vary my theta parameter from 0.001 up to 4.0 and see what happens. So on this graph, you've got the number of elements and the time of the simulation. And those 2 lines at the top, they represent small thetas and correspond to this case, this run. This red line corresponds to this simulation, and the magenta or light blue corresponds to that one. Maybe I'll show that again. Yeah, you can see how it develops. What I want to point out that depending on theta, the behavior of the behavior of this scheme or the element count changes. The behavior is different. So for those 2, for low thetas, my element count keeps increasing, even though this feature is already, well, sort of at the bottom boundary here. The red line stabilizes, so this one sort of stabilizes after some time, and the light blue tends to go down. Now the question is, which of those approaches is actually the correct one? Either this one, where we put a lot of elements, even here in the wake, maybe that one, which nicely encapsulates all the features we think we like to encapsulate, or maybe we push it even further and just have the refinement at the very center of this feature and don't really care that much about anything else, so those rotors and stuff. So I thought it would be interesting to look at some norms and how do they translate into speed up. So what you see here is the speed up against the element ratio. And element ratio is the number of elements in the fully refined case divided by the average number of elements in each of AMR cases. And the blue line shows the ideal speed up, so the case where AMR has, you pay no cost for that. And which is obviously not the case, you always pay something. And that's what the green line shows. So for low theta parameter values and this middle one, you pay approximately 4–5% of your speed up. Your speed up is 4–5% less than ideal. If you go up to those high theta values, the speed up decreases by roughly 10%. Now, that's actually an interesting problem because in this case, the cost of AMR is not only the projection between meshes and actually computing your super simple criterion or actually doing the refinement, changing the mesh, but also evaluating those fluxes at non-conforming interfaces. And I haven't looked at, I haven't break this cost down yet, but I will look into that and see which is the dominant part. I suspect it might be the flux computation rather than moving data back and forth through the meshes, because that happens locally. So again, and now, so that's sort of that shows how much do we gain. So we can gain up to 9 times speed up by applying this algorithm. Now, what do we lose doing that? There is an L2 norm computed in the entire domain against the speed up, and we see that if we really need to keep our L2 norm, say, low, we can still get away with 4 or 5 times speed ups. If you want to, if you really care about speed, we can go up, and then our L2 drops to 10 to minus 3. However, somebody pointed out to me that in AMR, if we do our refinement around something, we really care about this something, and we don't care about anything else in the domain. So what if we compute the same norm, but only in the at those elements which are at the highest refinement level? So here it is. I did exactly that. I just picked the elements which are at the top refinement level, and the red curve shows the behavior of the L2 norm. So actually, we can get away. The norm keeps is somewhere around 10 to minus 6, up to speed up 6.5 roughly, and only then for this higher possible speed up in this case, it goes up to 10 to minus 5, which I think is a decent result. However, again, I did not think about this enough, because this approach might not necessarily be the best one, because this assumes that the region we have picked for computing the norm is actually the right region. And you can see, you could see in those previous cases that this theta equal, let me show it to you again. Yeah, over there. Let it develop. If you look here, this fully refined region actually, after some time, only is limited to the interior of our feature, and those vortices are not encapsulated in this finely refined region. So maybe there is something more that we need to investigate here. Anyways, so how about then we go a bit further, and I can imagine some people would not care about L2 norms, because at the end of the day, what is that? How about we concentrate on some significant features of this particular case? So let's say we can track the front of this current, or maybe some minimal temperature there is. And I did exactly that, and to my surprise, the front position is exactly the same in all those 4 cases, which I guess that doesn't say that this is so great. It just says that this is the front position is not that sensitive to the AMR. And if you look at at the minimum theta, minimum temperature variation, it sort of changes linearly with our speed up, so with the element count, which I guess is a reasonable result. But even for the highest possible speed ups, we considered it's within 0.01% of the fully refined case, which I think is pretty good. Right, so to wrap it up, some outlook of what we are doing and what we would like to do with this. I would really like to show to you some mountain cases today to convince you that this is actually has some future in atmospheric simulations. But I'm still working on those, so stay tuned. Soon I will show you something. And I'm also working at the moment to implement this AMR technique into CG framework, so that we can compare directly our DG and CG method and see, you know, which one wins in this context. I played around with GPUs a little bit, and I'm happy to talk to you about that. I can only say that basically to be able to do the GPUs efficiently, we still need to optimize some data structures we've got, because it's not that great yet, but we still can squeeze in some speed ups from GPUs. We have implemented shallow water equations to that, so we will analyze those cases too and show them to you soon. And now for the future, we had a master student, who started looking into multi-rate time stepping, because for now our time step is constricted by the smallest grid spacings. But we would like to have different time steps in different elements, of course. So we're thinking about that. We need to implement this approach, which is 2D for now, into our 3D MPI NUMA on the sphere and everything. And so we're definitely going that direction. And I would personally like to think, how can I reuse all the machinery I have for this AMR algorithm, and maybe try to do some multi-grid preconditioning with that. But that's like a long shot, and we'll see if I get there and when. So I'll stop there. I'll show you some eye candies maybe. I'm not taking responsibility for those, but it's nice to look at them. This is a shallow water case we are running. This is the mountain case, and to my unskillful eye, they look decent. Well, there is some mountain over there underwater. Okay, thank you very much.
I'm going to ask a question first. So can you just explain, so what is the reason for this 2-to-1 refinement restriction? Is that
probably
to make the flux calculation easier, or what?
Exactly that.
Right.
So two reasons basically. First of all, I want to keep my life easy, make my life easy, and I don't want to consider, like, a whole suite of projection matrices. I just want to create them once and just use the one matrix. Then I imagine, I didn't check that, I imagine that if I go with this ratio higher, so 3-to-1, there is an awful lot of non-conformity going on, and I would like to avoid that. Plus, the third reason, intuitively again, I think that having this element, having a gradual change of element size is the desirable thing to have. I wouldn't like to go from a super small one to a super big one in this context. So that is my feeling.
Okay, but the whole framework is possible with.
Yeah, absolutely. Theoretically, at least, it's possible to do go with 3-to-1, 10-to-1, different P refinement options on both sides. It's all theoretically possible.
Are there some questions? How
about 3-to-2?
Good point. Good point.
That would be smoother than the 2-to-1. Yeah.
Agreed. I mean, I'd never thought about it before. Sure. I think, okay, Kopriva in 1996 paper, he considered those kind of arrangements, so they are theoretically possible. I didn't look into them and how they actually work, because that's, one thing is theory, one thing is practice. But that's a good point.
Some other questions?
Could you show the first films on your...
First meaning density current? Or
Yes.
This one?
Yes. Can you play them now? Yes.
There they are.
Waiting for the end. What I don't understand is when the grid gets very sparse at the back, where the rotor is, how can you recover the shape of it? Look now. Yeah.
Oh yeah, what I didn't say is that the element is of 10th order. So there's 10 by 10 points inside. Therefore, it's not just, I haven't got like, you know, I haven't got that.
That's better.
Yeah, sorry for that. Well, the reason I didn't say that is just in Gerardo Restelli paper 2008, they sort of used that. So I reused this expression order, and I sort of assumed that that's the way to do it. But of course, I should say that to you that yeah, that's the 10th order element. So yes, that's how I can actually reproduce this rotor here. Yeah, because otherwise this resolution here is ridiculously large to do anything with that.
Maybe one more question whilst the next speaker is getting ready at the back.
By using DG, you have a very quite accurate error estimator, very cheap, given by the jump of the solution.
Oh, I would love to hear about that.
Yeah, but why don't you use that to assess?
Okay, so my philosophy. I mean, okay, I'm relatively new to this area, and when I came in, I decided to keep my life as easy as possible, and then therefore I decided that the error estimator would be the thing I would care about at the end. So let's say end user will care about that. And I will just design this algorithm and try to make it run, and then worry about it, how to make it run, you know, optimally using optimal error estimation, right? So absolutely, I agree that there's probably plenty of much better and possibly easy estimators. This just seemed to me as something very intuitive. I can easily check whether it works or not. Because, to be honest, I did this work like for the past year. So it was more concerned to me that the algorithm actually performs well, or like actually works, delivers a solution, rather than delivering the best solution.
Okay, let's thank Mikhail again.